determinant of the hashing, then I can easily plug in the values into this determinant. Okay. So let's see which one I want to look at in terms of computing the second order derivatives. So in order to compute the second order derivative, you already done the first order derivative. You don't need to go back to your very original function. Right? So you only need to look at these formulas here. I in fact also have this simplified formula right here. Right? So this is indeed a f of x without removing the factor, the exponential factor here. So this is my f of x, this is my f of y. Right? So I can also look at these two formulas, but they are not very friendly to work with. So I'm looking at this one. Okay? So fxx, fxy, fyx, and fyy. So let's see what they are. I'm probably in a big matrix here. So fxx, I'm taking the derivative for that product. So I'm still going to use the product rule. All right? So it's going to be minus 2x into minus x squared minus y squared, then multiply by 2y minus 4 x squared y. This is actually not all of them. So I also have a plus e to minus x squared minus y squared multiplied by the derivative with respect to x. So it's going to be minus 8 xy. Okay? So this is my fxx. Again, in the end, even though this formula seems scary, but we are only worried about its positivity, all right? We're only worried about its positivity, so don't be scared here. These exponentials, they are all positive, so they don't change anything in terms of the positivity. So I also have to compute fxy, so it's taking derivative with respect to y over there. I need a big
go ahead, do it.
Paperwork. Hopefully we have not done anything wrong before, so that would be pretty detrimental. So if I'm taking derivative with respect to y, so I still have to use the product rule. So it's e to minus 2y, e to minus x squared minus y squared. Hopefully we're all working together. Okay, so hopefully we're all working together. So this is a good practice. And then multiply by 2y minus 4x squared y. Then plus e to minus x squared minus y squared multiplied by 2 minus 4x squared. So this is our first rule. Second rule is going to be fyx. I'm supposed to get exactly the same answer, but if you're not sure yet, let's compute it in order to verify whether they're true or not. So fyx, now I'm looking at this function instead, right? So if we're looking at this function, I'm getting a minus 2x e to minus x squared minus y squared, then 2x minus 4xy squared, then plus e to minus x squared minus y squared multiplied by 2 minus 4y squared. Okay? So in fact, you don't need to worry about this exponential term. Right? So if you want to compare that, I have a minus 4x squared, I have a minus 4x squared over there. I have a plus 8x squared y squared. So I have a plus 8x squared y squared as here. I have a plus 2, plus 2. I have a minus 4y squared, I have a minus 4y squared right here as well. Right? So they are indeed the same. Again, exponentials are just there to be positive, that's all. So fyy, I'm going to take the derivative 4 minus 2y e to minus x squared minus y squared. So multiply by 2x minus 4xy squared. And also we have plus e to minus x squared minus y squared. Then derivative with respect to y, so it's just a minus 8x1. Okay? So this is our 2 by 2 matrix, and I want to find its determinant.
Good luck. Oh boy.
Good luck. let's see.
4y, that's about it.
The point is, if I'm simplifying this whole thing into a
No, thanks.
determinant, and I get a very massive formula. However,
Just maybe.
because when I solve the equation, I do have these factors to be equal to 0. Because I only care about critical points, all right? If I only care about critical points, I use the second order derivative. I can indeed use these two equations. Agree with me? I can use these two equations. And luckily, when I look at this entry, I do see this factor coming out quite frequently. 2y minus 4x squared y, this term is actually disappearing, right? Similarly, this term is also disappearing. So this guy is also equal to 0. This guy is equal to 0. So in the end, in fact, quite some terms are vanishing here. So this is at the critical points. It is just equal to e2 minus x squared minus y squared as a common factor for all, multiplied by minus 8xy. So I have 4 minus 2 minus 4x squared, and I have 4 minus y squared. Why am I doing this? 2 minus 4y squared, 2 minus 4y squared, and very last one is minus 8x1. Okay? So this is indeed a much simplified version for the second order derivative matrix, Hanschen matrix. And I have to specify I am at critical points. Okay? I am at the critical. You can compute the Hanschen matrix at any given point. Right? You can compute the Hanschen matrix at any given point. It's just at the critical point, it contains some additional information about the extreme values. So if I'm doing here, I can easily test these things. Okay, I can easily test these things. Let's use this. Let's see what we have. So at 0, 0, everything is going to be pretty easy here. So at 0, 0, I have the whole matrix to disappear. Right? So the whole matrix 0, 0.
0, 0.
Oh, not really. No.
2.
I have 0, 0, but I have the anti-diagonal term to be 2 and 2. Right?
Mm-hmm.
So at this point, it's going to be 0, 0, 2, and 2. So this matrix is going to be 0, 0 minus 2, 2 is minus 4. 4. Right? So at 0, 0, determinant is less than 0. So this will immediately tell me 0, 0 is a shadow point. Okay? So then I needed to see these ones. Determinant of square root 2 divided by 2, square root 2 divided by 2. Okay? So the point is at all the 4 different points over there, these anti-diagonal terms are all equal to 0. You see that? Right? These anti-diagonal terms are equal to 0, so it is actually quite easy to compute the diagonal terms. So I have square root 2 divided by 2, square root 2 divided by 2, so basically I have a 1/2 coming here. Right? 1/2 coming here, 1/2 coming from here, so it's going to be 16 minus 0, so determinant is positive.
Something positive.
Determinant is positive, and the first entry is also negative, right?
We don't even
positive.
have to.
So fxx evaluate as square root of 2 divided by 2, square root of 2 divided by 2 is equal to minus 4, so it's negative. So this says this point is local maximum. Okay? So it's a local maximum. You can plug in this point separately. So I want to save some time. This guy is going to be, they're all, so this is minus 1/2. So I have a positive, positive, and also positive. This is a local minimum, right? So when I plug in here, xy is equal to minus 1/2. Right? So these two terms are still equal to 0. This is minus 1/2. So I have a 4 and a 4 as the diagonal terms. Determinant is positive, first entry positive, so it's going to be a local minimum. Right? So it's a local minimum. So if I plug in this guy, I'm getting a local minimum as well. And very first, very last point, I have xy is equal to 1/2. It is going to be exactly the same case as the case right here. Right? So this is the local maximum. Okay, so this is the local maximum. So even though you're dealing with a lot of exponentials, you will only complicate your derivatives by in order of evaluating all those things. Doesn't really matter that much. Okay, so here is the point of the class. Essentially, it's a skill test, right? The principles are all the same. It's just a matter of how you can compute. So I have a couple of more examples to show you. One of them is really about another application of this optimization. So in the very beginning, I said this section is about optimization, but I haven't optimized anything yet. Right? The only thing we have done is to find extreme values. We haven't optimized anything. So here is one problem. So it says if I am at a plane, x minus y plus z is equal to 3. Immediately you should know this is a plane. All right? 3 independent variables governed by one equation, all linear, has to be a plane. And I want to find the point on this plane that is closest to the point 2, 2, and 2. So if you really want to draw the picture, this is what the picture looks like. I have a point 2, 2, 2. Okay? I can easily check this point is not on the plane, right? Because I plug in, this is not a true equation. So 2 minus 2 plus 2 is not equal to 3. So this point is not lying on the plane. So this plane is somewhere else. Okay? So the point is somewhere here. Okay, so this is, let's say, 2, 2, and 2. Okay? So given any point sitting on a plane, you can find a distance between these 2 points. All right? So if I move this point on the plane, the distance can increase or can decrease. So I wanted to optimize this distance in terms of finding the shortest distance. You can easily find this distance to be as large as possible. You can make this point move to infinity on the plane. You can make the distance to be shortest by choosing one particular point. And in fact, the point you can choose has to be having a property. If you line these two, it is going to be orthogonal. Okay? If you line the point sitting on a plane which has the shortest distance with another point outside the plane, this line has to be orthogonal to the plane. But we can actually use the second order derivative test or the first order derivative to actually find this point. Okay? So we know the distance between 2 points. I have the distance between a point 2, 2, 2 and xy is always equal to x minus 2 squared plus y minus 2 squared plus z equals minus 2 squared, and then square root. All right, so this is actually the quantity I want to minimize. Okay, optimize basically means you can minimize it or you're maximize it. I want to minimize this quantity. Okay, I want to minimize this quantity with the constant that x minus y plus z is equal to 3, right? So naturally, I have one quantity with 3 variables, and we have talked about how to do 2 independent variables. You wanted to translate this guy into, you want to translate this problem into an optimization problem involving 2 independent variables, all right? So you have one constant, so naturally you wanted to, for instance, replace c by x, y, and into this formula, all right? So this is the way I can do it. So x minus 2 squared plus y minus 2 squared, then plus z is equal to 3 minus x plus y. So it's going to be 3 minus x plus y divided by 2 squared, then square root. Now I have 2 independent variables, and I don't need to worry about the plane at all because I already used the equation of the plane. Okay? I need to minimize this function, which means I need to find the critical point of this function. And that critical point is exactly going to be the point where you will achieve a minimal or maximal distance. And this is the only critical point. Okay, because there's no way you can achieve the maximum distance. You can go as long as possible. So you don't even need to use the second order derivative test to know the critical point you find has to be the minimizing. Okay, but we can actually check that. One point I want to make is this function involves square root. We already deal with exponentials. If I want to find a critical point for this function, I need to take derivatives, right? I have to take the derivative for square roots. I'm not happy about that, right? You're not happy either. You're going to take a lot of the derivatives, right? However, I know if I minimize the square of the distance, I will minimize the distance as well. Right? So indeed, I don't need to minimize this function. I can minimize d squared. The reason is d as a distance is always a positive quantity, right? So if you have negative quantity, it's not that easy. Right? D squared is minimized. D can be negative, then it is not a direct relation between these two optimization problems. I know distance is always positive, so minimizing the square root is the same thing as minimizing this new function. So I'm going to call this function fxy. Is equal to x minus 2 squared plus y minus 2 squared plus 1 minus x plus y squared. It becomes much, much easier to deal with. As long as you see polynomials, this is your best friend. This is your best friend forever in calculus. Okay? You can take the derivative, first order derivative, both of them vanishes. You can solve the system of two equations. You'll be able to find the equation. And then that critical point, you'll be able to find a critical point. That critical point is definitely where you can achieve the shortest distance. If you don't believe it, you can actually take the second order derivatives and compute the determinant at the given point. You can actually see by using the criteria of the form, it is indeed a minimizing problem. So I'm not going to do the following problem. I just give you fx is equal to 0, fy is equal to 0. These two equations will give you the critical point. Their critical point is definitely going to be where you can achieve the shortest distance. Okay. So in order to check that, you can use the second order derivative test to see whether it is indeed a local minimum. Okay. What I'm saying here is